Hi everyone to another tutorial, Intermediate Microeconomics, and today we're going to deal with the exercises, at least some of them, of chapters 5 and 6 of the book. And this is the program of today, number of exercises from chapter 5 and only one from chapter 6. So, what we will learn in this tutorial is we will deal with uncompensated and compensated demand curves. So uncompensated, or also called Marshallian demand functions, when income is held constant, versus compensated demand functions, or also called Hicksian demand curves, where the utility level is held constant. So we stay on the same indifference curve. What we also learn is how to use the uncompensated demand function to compute the indirect utility function and the expenditure function. We will come to Shepard's lemma and how to apply Shepard's lemma to find the compensated demand function, disentangling the effects of a price change using Slutsky's equation, and also we will consider consumption choices, not having a specific utility function in mind, but look at revealed preferences, and we will do an application of the weak axiom of revealed preferences, also called WARP. And finally, we will distinguish between gross and net substitutes and complements, and define when two goods are complements, substitutes, and when are they net complements, and when are they gross complements. Okay, so let's get started with the first problem, problem 5.4, which starts with a very familiar utility function and asks you to do a couple of things that are maybe less familiar to you. So we have a simple Cobb-Douglas utility function that's given here, and question A asks you to compute the uncompensated demand function, the indirect utility function, and the expenditure function. And we will do this step by step. So the key concepts in this exercise are the uncompensated demand functions. So the definition is given here. It's the optimal consumption level of good X and good Y as functions of the prices and income, capital I. And so this is the notation. Importantly, Marshallian demand functions are a function of prices and income. Then we have the indirect utility function. So we just plug in the Marshallian demand functions into the direct utility function, and we arrive at the indirect utility function. So we get this expression over here. Utility also ultimately a function of prices and income. Then the expenditure function are the minimum expenditures that we need to make in order to attain a certain utility level, given a particular set of prices. So this is the expenditure function, and the expenditure function and the indirect utility function, they are closely related to each other, as we will see, because they are each other's inverse. So those are the key concepts, and now start with our two-step program to solve question A. So what we will do, or what you might have done in preparing this chapter, is first to set up the Lagrangian function. And if you've done so, it should look something like this. And then you take first order conditions with respect to the goods X and Y and with respect to income, and you arrive at the three equations that are given here. Now, final thing that you need to do in step 2 is to solve in order to get the uncompensated demand function. So we need to solve for X and Y. But of course, the first parameter, the lambda, is a bit of a nuisance because we want to get rid of it. How to do that? Now, we rewrite the first two first order conditions such that we have lambda on the right hand side and all the other stuff on the left hand side. So then equation 1 becomes lambda is 0.3 divided by px times y over x to the power 0.7. Second equation, lambda is 0.7 divided by py times x over y to to the power 0.3. On the left-hand side, we have, in both cases, a lambda, which means that if these two things are by definition equal, then the right-hand side must also be equal. So we can equate the right-hand side of equation 1 to the right-hand side of equation 2, and we arrive at the expression that is given here. And you could also bring the py from the right-hand side to the left-hand side in order to arrive at py times y, and then we flip the 0.3 to the right-hand side and the 0.7 as well, equals 0.7 over 0.3 px times x. Now we've gotten rid of the lambda, and we have still two unknowns, x and y, but we know how they are related to each other at given prices px and py. And what we can do now is that in the budget constraint, we replace the py times y by the expression over here. So in the first order condition, we've replaced this part over here by what is given at this point. So to do that, we plug it in and we arrive at income should be equal to our expenditures to good x plus our expenditures to good y, but now as a function of px times x. And we solve this equation for x. And that gives us the Marshallian demand for good x. And it equals 0.3 times income divided by px. Similarly, we can solve for y, or we can, using this expression over here, once we know the x, we can plug in this value in order to solve for y star. And doing so, we get y star is 0.7 income divided by py. Now, this is nothing new to you, because in fact, that for a Cobb-Douglas function of this specific form, to the power 0.3 to the power 0.7, the Marshallian demand functions look like this. This is something that you've seen before. For example, in example 5.1 of the book. And as always, and this says that with this Cobb-Douglas function, you will spend 30% of your income on good x, and you will spend the remaining 70% on good y. So now we have the uncompensated demand functions, and we need to continue finding the indirect utility function. Again, 2 steps. So we collect the ingredients that we need to find the indirect utility function. Now, first element is the direct utility function, which was already given in the exercise. And the 2 other elements are the Marshallian demand functions for good x and y that we obtained in the previous step. And what we will simply do in order to arrive at the indirect utility function is to plug in these expressions into the direct utility function. And doing that, we get the following: the indirect utility function, so utility function as a function of prices and income, equals 0.3y divided by px to the power 0.3 times 0.7y divided by py to the power 0.7. And then you can simplify a little bit using your calculator, and you arrive at an expression like 0.54 px to the power minus 0.3 py to the power minus 0.7 times income. And indeed, here you see only prices and income. So this is an indirect utility function. Then finally, in question A, we need to solve for the expenditure function. So, and as noted at the beginning of the lecture, the expenditure function and the indirect utility function are each other's inverses. So what does it mean? Well, we have that the indirect utility function is equal to the expression over here. And we can now find the expenditure function by rewriting this indirect utility function, solving for income I. So we put all the things here in front of the y. We bring it to the left-hand side. We interpret the income as the minimal expenditure E that is needed to achieve a given utility u, and we arrive at this expression over here for the expenditure function. And by definition, the expenditure function should be a function of prices and utility, and it is. And that brings us to the end of question A. So we're done with that one. And now we can continue with question B. And in question B, we need to use the expenditure function that we've calculated in the first part together with Shepard's lemma to compute the compensated demand function for good X. So not for good Y, and that would be, you would do too much work if you would also do this for good Y. We only need to do it for good X in this exercise. Okay, so some refresher. We have the Marshallian demand functions that we considered in part A, keeping income fixed and looking for the optimal consumption bundle. And now we keep utility fixed and we look at compensated demand functions, which are the optimal consumption bundle at a given indifference curve. So, and the compensated demand functions are useful and they have solid theoretical foundation because they keep the utility level constant and they illustrate substitution effects from one good to the other. And they, because they keep utility constant, they abstract from the income effect. They keep it out of the picture. Okay, so what is Shepard's lemma? So Shepard's lemma says that the compensated demand for a good X can be found by partially differentiating the expenditure function with respect to the price of, in this case, good X. And of course, given that you already had derived the expenditure function in part A, Shepard's lemma is pretty useful in exercise B in order to find a compensated demand for good X. Now, why does Shepard's lemma hold? On the in the digital learning environment, I put a short note on the envelope theorem. Envelope theorem is also discussed in chapter 2 of the book. And in this note, I explain you why Shepard's lemma, where it comes from, and why it needs to hold true. So you can check that. And the basic idea is that once you are at the optimal consumption bundle, so you are at a point where your budget constraint is tangent to the indifference curve, then only the direct impact of a price change Px matters on the objective function. And in this case, the objective function are the expenditures. So if you are at the optimum and the price of good X, say cheese, increases, then what is the impact on your expenditures? Now, first, there is a direct impact. Suppose that you buy 10 units of cheese and now cheese becomes, say, a very small amount, so 1 cent more expensive. Then your total expenditures, the direct effect is that your total expenditures will increase by 1 cent times 10 units that you buy at the optimum. So 10 cents is the direct effect of the price increase. Then there is an indirect effect of the price increase, being that because the price changes, you will change your consumption of cheese. So you will change your X. But given that we start out at an optimum, this effect is quite negligible. So at the optimum, it's the direct effect that matters. And the direct effect of this small price change is equal to the number of units of, say, cheese that you consume. So, Shepard's lemma. Okay, now let's apply it. So, we already derived the expenditure function, and Shepard's lemma says that if we simply take the partial derivative of this expenditure function with respect to X, then we arrive at compensated demand. Well, doing that, meaning you pre-multiply the 1.85 with the 0.3 in the power, you reduce the power of 0.3 by 1, so you get power px to the power minus 0.7, and we end up with the expression here at the bottom of the slide. Okay, so far so good. And we've solved both questions A and B. Now in question C, we come to maybe the most complicated part of this exercise. So we again build on the results that we derived in question B, together with the uncompensated demand function that we found in question A. And we need to use both elements to show that the Slutsky equation holds for this case. Now, that is instructive because the Slutsky equation is rather abstract. You've seen derivations of the Slutsky equation, but you might think, still I don't know really why that holds. Now, what this question asks you to do is show by an example that in this particular case it holds. And of course, it also holds in all other cases. So what is the Slutsky equation? So it's a mathematical representation of the partial derivative of the uncompensated demand with respect to prices. So how does a change in the price of good X affect the number of units of good X that are bought? And to derive the Slutsky equation, the starting point is that you have an expenditure function. The expenditure function, by definition, as given here, tells you this is the minimum amount of income that I need in order to attain a utility level U bar. So that means that the compensated and the uncompensated demand functions are related in the following way. So the compensated demand for a good, given the prices and the utility level that I want to obtain, what is my optimal consumption of good X? Well, it's identical to the uncompensated demand for good X. So the number of units of good X that I would buy if the prices were the same, Px and Py, but my income would just be that income that would allow me to reach this indifference curve associated with the utility value U bar. So now we can differentiate both the left-hand side and the right-hand side of this equation with respect to Px. And note that in the left-hand side, the Px only appears directly in the function, and in the right-hand side it appears and in a direct way and indirectly through the expenditure function. So differentiating with respect to Px gives for the left-hand side this expression, and for the right-hand side this one over here. And we can rearrange, we can bring this second term in the right-hand side to the left-hand side, and we get the expression that is given here. And then in the final step, just like in the lecture, we notice that at the optimum, so the Shepard's lemma says that this partial derivative, or this one, is identical to the compensated demand. At the optimum, compensated demand is identical to the uncompensated demand, and that follows from the equation that we started out with. And we replace the expenditure by income, and that gives us the Slutsky equation. Now we're going to apply this equation. So again, we collect all the ingredients that we need to calculate it. This is what we derived in the preceding, and then we can derive the total effect of a price change in the total effect, that's the effect on the uncompensated demand, taking into account both the substitution effect but also the income effect. It's the derivative of the uncompensated demand with respect to Px. So we take the derivative of this expression over here. It's quite simple, and we have the total effect. To get to the substitution effect, we need to take the derivative of the compensated demand function that compensates for any changes in income and only looks at the substitution effect. So we remain on the same indifference curve. So we take the different derivative with respect to the compensated demand. So we already had that expression over here. So taking the derivative with respect to Px gives us this expression over here. But this still has the utility level U in there. And we need to find out, okay, what utility level is associated with the indifference curve that we consider. Now, that's not that complicated because we can replace the U over here with the indirect utility function, which is in terms of prices and income. And doing so the indirect utility function is the expression given here. So we insert that expression for the U over here in order to arrive at this expression, and then you can wrap together the different terms with the Px's and the Py. Actually, the Py's to the power 0.7 to the power minus 0.7, they cancel out, and we arrive at a substitution effect equal to minus 0.21 times income divided by Px squared. Okay, almost there. So then in step 4, we need to compute the income effect. And the income effect of the price change is equal to minus x times the differential of x with respect to income. Now, that term is not that complicated, so we take the uncompensated demand function and we differentiate with respect to y, leaves us with 0.3 px. We substitute the x over here with the expression for the uncompensated demand function, and we arrive at minus 0.9 I over px squared. And these px squared, the p should be small and not in capitals, but take that into account. It's a typo. So now we can collect the three and see whether indeed the total effect is a sum of the income effect and the substitution effect. Now let's do that. We plug all these three elements into the Slutsky equation, and we obtain that the minus 0.3i over px squared should be identical to minus 0.21i over px squared minus 0.09i over px squared. And you can check that indeed this holds. The left-hand side is identical to the right-hand side. So for this example, the Slutsky equation holds.